Okay, we're going to look at the last few sections here for chapter 20. And the first one, section 5, is all about free energy and redox reactions and spontaneity. So we'll take cells, use redox reactions that proceed spontaneously. Okay, remember that the E naught is your reduction minus your oxidized, your cathode minus your anode. All right, well, if that turns out to be a positive E, that one is spontaneous. If it turns out to be a negative E, that one is going to be non-spontaneous. Okay? Now we're going to look at the activity series and reduction potentials. Okay, your activity series list goes from easiest to oxidize to hardest to oxidize, whereas a reduction potential list goes from easiest to reduce to hardest to reduce. So they are the exact opposite. So our older activity series that we looked at last year for chemistry, okay, was the metals that are easiest to oxidize or easiest for that particular metal to replace something else. Reduction potentials are the exact opposite. They are reductions, okay? So in this example with my lithium here, okay, I have lithium and NaCl. Lithium goes from a 0 to a positive charge, okay, which means it lost electrons, so it is oxidized. Lithium is very easy to oxidize. It really likes to replace that sodium. It's more active, okay, so it'll be higher on the activity series. But it will be the exact opposite. It'll be very low on the reduction potential list. It should actually be very towards the bottom. Okay, so think of it as an upside down activity series. So let's look at a couple of examples here. It says using standard reduction potentials in table 20.1, which is basically the green standard reduction potential list that you have on the equation sheets. Okay, determine whether the following reactions are spontaneous under standard conditions. Okay, so let's look at the first one. Look at A. All right, here's this one with copper. Okay, copper goes from a 0 charge to a 2+ charge, okay, which means that copper is oxidized. So my Cu is the oxidized, which means that my reduction one, okay, better be the hydrogen. Okay, and the hydrogen goes from a 1+ to a 0, so it is reduced. Okay, so if copper is the one that is oxidized, okay, remember when we do our E naughts, we do cathode minus anode, okay, which means I need to look up on my list and find these numbers, okay. Well, the one for hydrogen is 0, the volts it'll tell you, and the one for copper it'll tell you that it's 0.34. So I do cathode minus anode, I do 0 minus 0.34, and you should get negative 0.34 volts. Since it is a negative one, okay, here, a negative voltage, this one is non-spontaneous under standard conditions. So I'll go ahead and look at that second one there with chlorine. And what you should notice about the one with chlorine, okay, is that your chlorine is the one reduced, the iodine is the one oxidized. So I find my numbers for that. I have 1.36 minus 0.54. It's going to be 0.82. That one is positive, so it is spontaneous. Okay, so now we're going to look at EMF, which is my electromotive force, and my delta G. Okay, delta G tells you your spontaneity at a constant temperature and pressure. Okay, so remember that my delta G naught will tell me how spontaneous something is. All right. What we did is we get these new kind of equations that we can actually use, and it is this delta G equals negative NFE. Okay, if it's at both knots, they're at standard. Okay, the F is usually like a fancy looking F, okay, something kind of like that, usually on your equation sheet. Here I'll draw it as an uppercase F. Okay, that uppercase fancy F is Faraday's constant. It's how many coulombs per mole. Okay, coulombs are a fancy unit for charge. Say fancy, it's the unit for charge. Okay, and it is the charge of a mole. Well, a mole of what? Actually, the charge of a mole of electrons. Okay, so that's how much charge 1 mole of electrons actually has. Okay, N is the number of electrons transferred, and then E or E naught is your reduction potential or cell potential. Okay, so we kind of use this to relate our E to our delta G. Okay, so let's try that here with this next one. So we're supposed to use the standard reduction potentials listed in the table, calculate the free energy change for delta G, and the equilibrium constant K for the reaction. Okay, so we can kind of use our E then that tell us our G value, and then our G value will help tell us our K value. Because, remember, delta G naught is equal to NFE naught, okay? And I want my K, which means we also know that delta G naught equals negative RT natural log of K. So I can use the one that I know with the E, figure out my G, and use that G, figure out my K. So let's go ahead and let's try that. All right, so we start off with knowing our E naught. Well, if I need to know my E naught, that means I need to know which one's the cathode, which one's the anode. Well, if we look at that reaction, okay, and it's actually down here at the bottom. All right, I have my 4 Ag plus O2. It's going to go to Ag plus and 2 waters. So which one's oxidized, which one's reduced? Okay, well, my Ag, okay, goes from being 0 to being a plus. Okay, if it goes from being a 0 to a plus, that means my Ag is the one that is oxidized. So this is my one here that is oxidized, which means I got to figure out which one is reduced. Okay, well, my O2 should be the one that is reduced because it goes from a 0 charge as an O2 and then a negative 2 charge when it's over here with water. So Ag is the one that's oxidized and O is the one that's reduced. So we're doing cathode minus my anode. So I look up my values, okay, and I should find that my cathode value, which is the O2, is 1.23. Minus my anode, which is 0.80. Should give me a voltage of 0.43 volts. I use that 0.43 volts then, and I'm going to find my delta G. So delta G equals negative R, which is 8.3. Oops, sorry, not that one, wrong one. My delta G equals my N. And how many electrons do I have going on here? I have 4, okay? Because you have to look at the total. You should see here that I have 4 H plus I have 4 Ag plus there. I'm moving around 4 electrons. So negative 4 is my N. F is that Faraday's constant, which is 96,000, depending on which book you're looking at. I use 485. It's also rounded to 96,500. Okay? Times my E naught, which is 0.43. And my value for G becomes a negative 165,954, and that's the number of joules per mole. Well, then I take this one, and I now need to find my K. Well, I know my G value here is negative 165,954 equal to negative R, 8.314, times my temperature. It told me in the problem that it's 298. My natural log of K. And all I got to do is divide and solve for K. And my K value is really, really large, 1.23 times 10 to the 29th. Okay, so go ahead and try the next one, which is very similar to the one above. Okay, so we see our reaction there, okay, and we have a different delta G value, same E, different delta G, and a different K.